Have you ever wondered why some elements are more reactive than others? Or why metals like iron are so different from nonmetals like oxygen? These questions all come down to the patterns in the periodic table. The periodic table is not just a chart of elements, it's a map that reveals the changing properties of elements across periods and down groups. By understanding these trends, we can predict everything from reactivity to physical properties like density, melting point, and boiling point. In this session, we'll focus on how these properties vary in a systematic way, not only across a period but also down a group. This will give us a deeper insight into why elements behave the way they do in reactions and how they are used in daily life. As we move across a period from left to right, elements show an increase in density and melting points, but there's a catch. This trend only continues up to a certain point before it slightly decreases. For instance, look at lithium, which has a density of zero point 0.5 grams per cubic centimeter and a melting point of 181 degrees Celsius. Moving across the period, we reach carbon, where the density increases to 2.3 grams per cubic centimeter and the melting point skyrockets to 3727 degrees Celsius. This happens because of the increasing number of protons in the nucleus, which pulls electrons closer, strengthening metallic or covalent bonds, thus increasing the melting and boiling points. But then, elements like chlorine and argon show much lower melting and boiling points due to their molecular structures that exhibit weaker forces between atoms. Now, let's look at how these properties change as we go down a group. Take the alkali metals as an example. Lithium, sodium, and potassium show an interesting pattern. Their density increases as you go down the group, but their melting and boiling points decrease. For example, lithium's melting point is 181 degrees Celsius, but potassium's is only 63 degrees Celsius. This happens because as we move down a group, the atomic size increases and the electrons are farther from the nucleus. The metallic bonds become weaker, which makes it easier for the atoms to break apart, lowering the melting and boiling points. This is why metals like potassium have lower melting points compared to lithium. Their larger atoms don't hold on to their electrons as tightly. Just like physical properties, chemical properties also follow clear trends in the periodic table. For example, oxides across a period change from strongly basic on the left to strongly acidic on the right. Think about sodium oxide, which is strongly basic, versus silicon oxide, which is more acidic. Similarly, hydroxides shift from strong bases to amphoteric and then acidic as you move across the table. This shift happens because the metallic character decreases and the non-metallic character increases as you go from left to right. Also, the strength of oxyacids increases as we move across a period. For instance, a weak oxyacid like carbonic acid becomes a stronger oxyacid like nitric acid as we move from left to right. But if you look down a group, the opposite happens. Oxides and hydroxides become more basic and oxyacids generally weaken. Have you ever wondered why some elements are stable while others are radioactive? The answer lies in the neutron to proton ratio, also called the N to P ratio. For example, light metals like sodium and potassium have stable isotopes because their N to P ratio is balanced at around 1.1. However, heavy elements like uranium have an N to P ratio higher than 1.5, making them unstable and radioactive. This ratio is crucial in determining whether an atom is stable or prone to decay. Elements with an unstable nucleus release energy in the form of radiation, undergoing alpha, beta, or gamma decay, depending on the situation. This is why we have radioactive elements like uranium that decay over time. Their high N to P ratio makes them unstable. Let's dive into some key values that help us understand the behavior of elements. First, atomic size. As we move across a period, atomic size decreases because the increasing number of protons pulls the electrons closer to the nucleus. On the other hand, moving down a group, The atomic size increases due to the addition of electron shells. Next, ionization potential, or the energy required to remove an electron from an atom. This increases as we move across a period because the electrons are held more tightly by the nucleus. Similarly, electron affinity, which refers to the energy change when an electron is added to an atom, becomes more negative across a period. And finally, electronegativity, the ability of an atom to attract shared electrons in a bond, increases as you move across a period and decreases as you move down a group. All these trends are interconnected and essential for predicting how elements will react and bond. To recap what we've learned today, both physical and chemical properties follow clear trends in the periodic table. From left to right, we see an increase in density, melting points, and boiling points, followed by a decrease in these properties as we move down a group. Chemical properties such as the acidity of oxides and the basicity of hydroxides also change predictably across and down the table. The neutron to proton ratio plays a crucial role in determining whether an element is stable or radioactive, and atomic size, ionization potential, electron affinity, and electronegativity give us insights into element reactivity. By understanding these trends, we can predict the behavior of elements and design new materials with specific properties. I hope this session helped you see how chemistry is more than just equations. It's the invisible force behind everything from the metals we use in tools to the chemical reactions that happen inside our bodies. Catch you in the next class where we'll explore more fascinating topics in chemistry.